So this is the next video. It is on the transmission lines. So if you know everything about the electromagnetic waves, EM waves, so it will be, the analysis is very simple for the transmission lines. There we have talked about the EM waves, electromagnetic waves. Here we talk about the VA waves, voltage and current waves. Here the transmission lines are nothing but here the lines are conductors. They are the lines are the conductors. That is the point how to understand. Okay. So that there the medium was any general medium like dielectrics and also free space. There mainly we consider there. Okay. So but the conductors are not suitable for propagation of the EM waves. Okay, the conductors are not suitable for the propagation of EM waves. So that's why we use VI waves to propagate. We use we transmit the VI waves in the transmission lines. So we will make use of the more conductivity. So to make use of the more conductivity, we use the transmission lines. Okay, so this is the thing. You should understand that. Okay. So here very important parameters you should consider, that is, suppose if you take the EM waves, there are mainly three medium parameters. What are the medium parameters? Sigma, epsilon, mu. Sigma, epsilon, mu are the main three important parameters. Here very important parameters here are four parameters here. Okay, those parameters are called as the material constants. Okay, those are called as the material constants. Here we call this one RLGCs. RLGCs are called as the primary constants. They are the material constants. These are called as the primary constants. That means each and every transmission line will be characterized by RLGCs. So this is the thing you should understand that. So these are called as the primary constants, and also these are all distributed parameters. What is meant by distributed parameters means these are not simple RLGCs. Resistance, inductance, conductance, capacitance. Okay, they are not the lumped parameters. These are the distributed parameters. That means the resistance, inductance, conductance, capacitance are calculated per unit distance. Okay, so that's why these are called as the distributed parameters. Okay, so the units of these RLGCs are called as mho per meter, Henry per meter, ohm per meter, and farad per meter. Okay, so whenever if anything is represented as a distributed parameter means, okay, always it will be measured per unit distance. That is the point you should understand. Okay, the primary constants are called as the RLGCs. Material constants are called as the sigma, epsilon, mu. What are the units of sigma? Units of sigma are conductivity, right? So mho per meter means this one, mho per meter. Okay, what are the units of epsilon? Ohm, farad per meter. What are the units of mu? Henry per meter. That means these are similar to the material constants only. Okay, so that is the point you should understand that. But only there are 3 parameters, but here there are 4 parameters. The extra parameters are here. Okay, there is no parameter for ohm per meter there. Okay, but here there are ohm per meter, Henry per meter, mho per meter, and farad per meter. So these are the 4 parameters you should consider. Okay. See, one thing you should remember, that is, okay, these RLGCs, even it may be lumped resistance, capacitance, inductors, or maybe distributed resistance, inductance, capacitance, okay, conductance also, they are not dependent on the electrical parameters, but they will be dependent on the physical parameters. This is the thing you should understand. Okay, now come to this. If you take a coaxial cable and parallel line wire, mostly they are asking on the coaxial cable and parallel line wire, so that's why we have to focus on this. Okay, so if you take a coaxial cable, the capacitance, the distributed capacitance of already we know. So what will be the capacitance of a concentric cylinders? Because why I am taking the concentric cylinders? Because the coaxial cable is the geometry of the concentric cylinders. There will be inner conductor, in between there will be a dielectric medium, and after that there will be an outer conductor. So it is looking like a concentric cylinders. So that's why we have to compare this geometry with that. Okay. So that's why already we know concentric cylinders capacitance. What is the concentric cylinders capacitance? 2 pi epsilon h divided by ln b by a. Already we know what is b. B means the outer conductor radius. Okay, and B is the A is the inner conductor radius. Okay, radius from the center reference line to the inner conductor radius is A. B is the radius from reference line to the outer conductor. Okay, so this is called as the capacitance of a coaxial cable. So what is the capacitance of a coaxial cable? C is equals to 2 pi epsilon divided by ln B by A. Right? Why there is no H here? Okay, so if you take the concentric cylinders capacitance, there will be one H here. Okay, but H means it is the length of the cylinder, but we are talking about the distributed parameters, and this H will go here, means capacitance per meter. Okay, means farad per meter. So that's why you have to write 2 pi epsilon divided by ln B by A. Okay, if the length is very high, then we will not include the length here, because all the transmission lines are very far length transmission lines. So that's why we don't include L here, the length of the line. So similarly, if you write the capacitance for the parallel line wire, C is equals to pi epsilon divided by ln D by R, right? So this is the capacitance for the parallel line wire. Suppose if you take a parallel line wire for the capacitance for this lumped parameters, so here you will get C is equals to pi epsilon divided by ln D by R, right? So in the similarly the H will go here, so you will get C is equals to pi epsilon divided by ln D by R, right? Similarly, this is the inductance. Inductance of the coaxial cable is mu divided by 2 pi ln B by A. L is equals to mu divided by ln D by R. What is meant by this D and R? D is the distance between the two lines, parallel lines, and R is the radius of each line. Okay. So these are the very important expressions. You should remember this. Okay. So now if you multiply this one and this one, what happens? If you multiply this one and this one, L into C, what happens? 2 pi will get cancelled, ln B by will get cancelled, finally you will get mu epsilon. Or otherwise, if you multiply this one and this one, again you will get mu epsilon only. ln D by R will get cancelled, pi by will get cancelled, mu into epsilon will be there. So that means for any line, if you multiply distributed L into distributed C, you will get mu into C, mu into epsilon. Okay, so this is a very important parameter. By this we will define the phase velocity. Okay, already you know what is the phase velocity. Phase velocity is equals to Vp is equals to 1 divided by root mu epsilon, right? So instead of writing root mu epsilon, here we will write 1 by root over LC. So you can also define the phase velocity by using the L and C. Okay, so these are the very important things you should understand that. The next one is VI wave equations on the transmission lines. So what are the VI wave equations? It is similar to the EM wave equations in the medium only. Okay, how the EM wave equations? Dou square E, already you know, dou square E by dou x square is equals to j omega mu into sigma plus j omega epsilon into E. Okay, dou square h divided by dou y square is equals to r plus sigma j omega mu into sigma plus j omega epsilon into h. Okay, so in the similar manner, here also we will define the VI wave equations on the line. But there are dou square by dou x square is there, dou square by dou y square is there, but they are electric and magnetic fields are orthogonally perpendicular to each other. So that's why there are two different directions. But here we are considering a single direction. Okay, the propagation is in the single direction. So that's why current and V, voltage and currents are in the single directions. So that's why, and voltage and currents are varying in X direction only. Okay, voltage and currents varying in on the line only. On the line means it is a single direction. Okay, it is not in the space. If it is in the space, then multiple directions will come. Okay, so because the voltage and currents are varying in a single direction, so that's why we have to take dou square v by dou x square, dou square I by dou x square. Okay, instead of j omega mu sigma plus j omega epsilon, here we have to write r plus j omega l into g plus j omega c. So this is called as gamma square. Already we know what is meant by gamma. Gamma is equal to propagation constant. So I am rewriting this equation by placing this one as gamma square. Okay, it is a differential equation. These two are the differential equations. One thing you should understand that already you know there must be, to generate a VI wave, there must be a time harmonic source. Okay, even it may be an EM wave or VI wave, there must be time harmonic source. Okay, if the time harmonic source is existing, then automatically the wave will be transferred into the wire. So there must be a time harmonic source. Without time harmonic source, there is no concept of the harmonics. Okay, so if the cause is harmonic and the effect is also harmonic, that is the point you should understand that. Okay, so this is dou square v by dou x square minus gamma square v is equals to 0, dou square I by dou x square minus gamma square I is equals to 0. So these are the two differential equations. Okay, if you solve these equations, you will get v of x and I of x. Okay, already you know there will be, it is the solution for general solution for the v of x and I of x, because it is a differential equation. If you solve this, you will get this kind of expressions. Okay, here one important thing you should understand that every wave is a, even it may be EM wave or VI wave, every wave, even it may be a VI wave or EM wave, as they are moving from the source, as they are moving away from the source, what happens? Its amplitudes will get decayed exponentially. Okay, so that means either V of x or I of x, okay, it is having two components, one is in positive direction, one is in negative direction. Okay, so both are exponentially decaying, mostly what? Exponentially decaying. Okay, so that is the point you should understand. So V of x and I of x both are exponential decays. So that means if you observe this is also exponential decay, this is also exponential decay. So on this line there will be two kind of waves, one is positive x directed wave, one is negative x directed wave. Already we know it must be exponential decay, this is also must be exponential decay. So that's why we can say this one as what? It is if it will be exponential decay if and only if x is positive. It will be exponential decay if and only if x is negative. So we can say this one as positive x directed wave, this can be said as negative x directed wave. So that is the important point you have to understand. So whenever there is a positive sign in the exponential, then we should know that it is a negative x directed wave. When there is a negative sign in the exponential, when there is a negative sign in the exponential, we should understand that it is a positive x directed wave, If there is a positive sign in the exponential, we should remember that it is a negative directed wave. Okay, because waves are exponential decay as they move away from the source. Okay, if you observe this, it is as time harmonic source and there is a load, in between there is a long length wire is there. So this is called as the transmission line. Okay, let us suppose the length of the line is L. Okay, so at x is equals to 0, I am putting a load here, and x is equals to L, there is a source, because the length of the line is L. So that's why it is x is equals to 0, this is x is equals to L. So this is the point always you have to understand. But if you take the EM wave case, that will be all the parameters or the analysis will be done from the source point of view. Okay, but if you come to the transmission lines, always the analysis will be with respect to from the load point of view. So that is the point you should understand that. Okay, so that's why we are naming, because the analysis is done from the load point of view. So that's why we have to write x is equals to 0 here. So that means we are at x is equals to 0 means I am at the load. Okay, in the EM waves, if z is equals to 0 or x is equals to 0 means, in the EM wave concept, if z is equals to 0 means I am at the source. That is the point. If you are talking about x is equals to 0 in the transmission lines, So here we are at the load point. So as x is increasing means x is increasing in this direction. Okay, x is increasing in this direction. So this is called as the positive x directed wave. This is called as the negative x directed. This is called as the positive x directed. Suppose if the wave is going in this direction, that is called as positive x directed. Suppose if the wave is going in this direction, this is called as the negative x directed. This must be very careful, because this is x is equal to 0, x is equal to 1, x is equal to 2, x is equal to 3, x is equal to L. So x increasing direction is positive x directed wave. So if you go in this direction, this is called as the negative x directed wave. Okay. Now, so this is called as what? This is called as, this wave is called as this wave. Suppose if the wave is going in this direction, means it is going from source to load. Source to load is called as the forward wave. But forward wave is which direction? Forward wave is in this direction, right? So that's why this forward wave is also called as the negative x directed wave. So this forward wave is also called as the negative x directed wave. This forward wave is also called as the, this forward wave is also called as the negative x directed wave. Right? This forward wave is also called as the negative x directed wave, right? And suppose if there is a negative terms are there in the exponential, that is called as the positive x directed wave. What is the positive x directed wave? In this direction. That means this is called as the reflected wave. Okay. So this is the V of x and I of x, and if you solve the equations for C1 and C2, C3, C4, we will get the final equations like this. V of x is equal to VL into ZL plus Z0 divided by 2ZL e power gamma x plus ZL minus Z0 divided by ZL plus Z0 into e power minus gamma x. Okay, I of x also IL into ZL plus Z0 divided by here 2 Z0 here 2 ZL here. This is an observation you should remember. Okay, and these are, observe this, e power gamma x plus Z0 minus ZL. Observe this. This is Z0 minus ZL. Here ZL minus Z0. Here Z0 minus ZL. So this is the voltage wave and current wave. So these are the two important points you should understand. Okay, so it is a voltage wave. For the voltage wave we will get ZL minus Z0 divided by ZL plus Z0. For the current wave we will get Z0 minus ZL divided by Z0 plus ZL. So these are the voltage and current equations on the line. So if you put at any value of x, if you put x is equal to 0, so this will be, if you have to put x is equal to 0 and you will get the voltage at the load. Okay, if you put x is equal to 0 in this, x is equal to 0 in this, then you will get the current at the load. That is the thing. Right? Now we are defining the impedance. What is meant by impedance? Impedance is equals to Z of x is equals to V of x divided by I of x. Okay, so it is represented as Z of x is equals to V of x divided by I of x. So this is called as the impedance at any x. So that means what? If you put any value of x, you will get impedance at that instant. So that's why this is represented as impedance at any x. So Z of x is equals to, if you rearrange these equations, suppose if you write, take the LCM ZL plus Z0 into e power gamma x plus ZL minus Z0 into e power gamma x, and you rearrange these equations, then you will get Z of x is equals to Z0 into ZL cos h gamma x, Z0 sin h gamma x divided by Z0 cos h gamma x plus ZL sin h gamma x. So what is the sin h cos h? These are called as the hyperbolic functions. Okay, so this is called as the Z of x at any, Z of x means it is the impedance on the line anywhere at any point. So you can get the impedance at any point on the line. So this is the generalized expression for the line impedance. Okay, now suppose if you want to find the input impedance for this line, for any line, if you want to find the input impedance means what? The impedance at this place. What is the at this place? What is the distance? Distance is L from the load. So that's why if you put x is equal to L, then this will be called as the input impedance. So this will be called as the input impedance. So Zn is equals to Z of x at x is equals to L. This is called as input impedance. So this is the entire thing. So already you should know that. So this is input impedance. So if you observe this, V of x and I of x, If V of x and I of x, there are two terms are there. Two terms are there means these two terms are exponentially decaying only. Okay, exponentially decaying only. So this is the common sense, right? So one is called as the forward wave, one is called as the reflected wave. So here it is called as the forward wave, it is called as the reflected wave. How can you identify it? It is called as the positive x directed wave. What is a positive x directed wave? Positive x directed wave means this one. Positive x directed wave means this one. So this one means what? This one, right? So positive x directed wave, this is called as the reflected wave here. Okay, so e power gamma x, this term, this is called as the forward wave. So this forward wave is negative x directed wave. Okay, don't get confused. If it is negative x directed wave, it must be reflected wave, right? So that means it is not. But here, the reason here is we are doing the analysis from the load point of view. So that's why the x increasing direction. Okay, so this will be the positive x directed wave. That means in this direction representing the reflected wave, in this direction representing the forward wave. Okay, so here it is called as the forward wave, here it is called as the reflected wave. Actually the reflected wave must not be present in any line. Okay, reflected wave, even if you take the EM waves or if you take the transmission lines, the reflected wave must not be present in the medium. Okay, so to vanish to make the reflected wave zero, what is the condition? To make the reflected wave zero, what is the condition? These all are constants here. See what we can do. The simple thing we can do, this is the reflected wave, right? The simple thing we can do that is ZL is equals to Z0. If you put ZL is equals to Z0 here, even in this or in this, okay, what you will get? ZL is equals to Z0, this entire term will be vanished. So this entire term will be vanished means this term will be vanished, this term will be vanished. So that means only you will get what? Only you will get e power minus gamma x, means what? Which kind of wave is? It is negative x directed wave will be existing. What is a negative x directed wave? This wave. Negative x directed wave is this wave, right? So this wave is nothing but what? It is a forward wave. Only forward wave will exist. There is no reflected wave. This kind of condition, if ZL is equal to Z0, that is called as the matched condition of the line. If ZL is equal to Z0, this is called as the matched line. So what is ZL means? The load impedance is equal to Z0. We will see what is Z0. Okay, Z0 is called as the characteristic impedance of the line. Each and every line will be characterized by one impedance, that is called as the characteristic impedance. Okay, suppose if the line is terminated with the characteristic impedance, if the line is terminated with the characteristic impedance, that means if the load impedance is equal to the characteristic impedance, then that is called as the matched line, right? So what is Zin? Zin is equals to Z of x is equals to Z0 is equals to ZL. If you do the small thing, what is that small thing? If you put ZL is equals to Z0 here, what happens? What is the Zin? Z of x is equals to how much? If you put ZL is equals to Z0, ZL is equals to Z0, this entire thing will get cancelled. Only you will get Z of x is equals to Z0. Z of x is equals to Z0. Right? What we are doing? ZL is equals to Z0. We are making this one. Anyhow, these two are equal. If you put like that. Okay? So that means Z of x is equals to Z0. Right? If Z of x Z0 means impedance anywhere on the line Z0 means, if you put this condition, so Zn is also Z0, because simply what we are doing, we are changing x is equals to L. Even if you change x is equals to L, x is equals to 10, x is equals to 100, x is equals to anything. If ZL is equals to Z0, then what happens? Zn is also is equals to Z0. So this is the thing you should understand. Okay? If we put ZL is equals to Z0, impedance anywhere on the line, even it may be load or in between or at the input, everywhere the impedance will be same, and that impedance is equals to the Z0. That impedance is equals to the Z0. So this is called as the matched condition. This is called as matched condition. If you see anywhere, if you put ZL is equals to Z0, then everywhere the impedance will be same. That is equals to Z0. Okay. Suppose if ZL is not equals to Z0, you will be having at different points, you will get different impedances. Okay. If ZL not equals to Z0, at each and every distance, different kind of impedances will be present. Okay, you cannot expect the impedances are same on the line. Okay, at load impedance, one impedance will be existing. Okay, and in between one impedance will be existing, and at the input one impedance will be existing. So you cannot say these all are equal. You cannot expect the impedance everywhere on the line is same, right? So this is what about the matched condition. So if the matched condition means what? There will not be any reflected wave. There will not be any reflected wave. Now one more important concept in this is short circuit and open circuit lines. What is the short circuit and open circuit line means? So what is short circuit line? If ZL is equals to 0, if ZL is equals to 0, then that is called as the short circuit line. Okay, if ZL is equals to 0, now what will be the input impedance? Already input impedance is this one. At X is equals to L, we should write this. So we have to write X is equals to L here, right? And if short circuit line means what? It must be 0. It must be 0. If these are all zeros, then the Z0 into sin H gamma L divided by Z0 into cos H gamma L. Z0 will get cancelled. It is tan H gamma L into Z0. So Zn is equals to Zs is equals to Z0 tan H gamma L. So this is the input impedance. It is the input impedance of the short circuit line. It is a very, very important thing you should understand. Okay, here gamma already you know, gamma is equals to propagation constant. What is gamma? Gamma is equals to root over r plus j omega L into g plus j omega c. It is called as the propagation constant. It is generally a complex value. It is generally a complex value, right? So this is tan H gamma L. Now if ZL is equals to infinity, if ZL load is infinity means the load is open circuited. Okay, open circuited means this is called as the open circuited line. Now what will be the input impedance of the open circuit line? Suppose if it is the short circuited, now input impedance will be this much. Suppose if it is open circuited, the input impedance at this line will be the input impedance of the line will be Z0 cot H gamma L. Okay, you have to put ZL is equals to infinity. Don't put ZL equals to infinity directly. You take the ZL common and cancel it out. Okay, so this is the thing. So Zin of the open circuit line can also be represented with ZOC. The Zin of the short circuit line can also be represented as ZSC. It is Z0 tan H gamma L and Z0 cot H gamma L. These are the very, very important relations. Okay, suppose if you multiply this one ZSC and ZOC, ZSC and ZOC, okay, is equals to Z0. Suppose if you multiply these two, what you will get? You will get Z0 square. So you take the under root, you will get root over ZSC into ZOC is equals to Z0. Okay, so this is called as the characteristic impedance is what is characteristic impedance? Characteristic impedance is the geometric mean of short circuited input impedance and open circuited input impedance. Okay, and this is one expression, and one more expression is Z0 is equals to root over r plus j omega L divided by g plus j omega c. It is similar to the intrinsic impedance of the medium. In the intrinsic impedance, eta is equals to root over j omega mu divided by sigma plus j omega L. Okay, but instead of 0 r there is 0. Okay, 0 plus j omega mu divided by sigma plus j omega epsilon. Okay, here inductance, conductance, capacitance, there mu, sigma, epsilon. Okay, so that is the point you should understand. So this is the gamma, and both are you can compare with the EM waves. The VI waves can be compared with the EM waves, and it will be very easy for you to remember. Okay, so this is the gamma and characteristic impedance and open circuit input impedance and short circuit input impedance. Okay, so these are the very, very and matched conditions. So these are the very important things. Okay, and one more important thing is from the transmission lines you will get very dead easy questions, so that you can each and every question will be solved. Okay, so that's why you must have some clarity about all these things. Okay, now come to the distortion and lossless and distortionless lines. So how can you get the lossless and distortionless line? Suppose if you go to the EM waves concept, okay, what will be the lossless line? If you talking about the lossless line means the propagation constant must be purely imaginary. The propagation constant must be purely imaginary means what? The alpha must be 0. Okay, alpha must be 0. Here also, if you are talking about the lossless line means there must not be any loss, means there must not be any alpha value in this. Okay. Now, first case, if you take R is equals to G is equals to 0. If R is equals to 0, G is equals to 0, then you will get root over J omega L into J omega C. The J omega will come out. So gamma is equals to J omega into root LC. So if you observe this, if R is equals to G is equals to 0, we are getting gamma as purely imaginary, and this is equals to J beta. Okay. If you make this situation, if R is equals to G is equals to 0, then this is called as the purely imaginary. Okay, that means what? It is called as the lossless line because alpha is equals to 0, right? Omega L is equals to, if omega L is much greater than R, omega C much greater than C. There is a possibility of getting a purely imaginary propagation constant. Suppose if omega L is very high when compared to R, omega C is very high when compared to G. Now also we will get almost purely imaginary propagation constant. Okay, you should remember that if you are getting a imaginary propagation constant means we are making the line lossless. Okay, so these lines are called as, if you are having any line having this kind of property, these called as high frequency lines. Okay, so if you go to the EM waves concept, how can you find whether it is a lossless line or not? So first of all, we have to identify the gamma. If the gamma is purely imaginary, then that is called as the lossless medium. And one more important thing is the intrinsic impedance. What is the intrinsic impedance? Intrinsic impedance must be purely real. If the intrinsic impedance must be purely real, then we can say that it is a lossless line. So already we know Z0 is equals to R plus J omega divided by G plus J omega T. So if you put these two conditions, any of these two conditions, then you will get Z0 is equals to root over L by C. This is real. This is real because inductance is a real, capacitance is a real value. So these two are real values. So that's why you will get the characteristic impedance as a real value. So already you know L and C value. Suppose if you take a coaxial cable, this is what? L and C. If you divide this one with this one and if you take a root, you will get 60 divided by root epsilon or L and B by A. Okay. Similarly, if you take a parallel line wire, L and C, if you divide L by C and take the under root, then you will get this one. So 120 divided by root epsilon r. So for all these cases, what is this Z0? Z0 is totally dependent on the physical dimensions of the capacitor and inductors. Okay, the physical dimensions of the line. Okay, it is a coaxial line cable and it is a parallel line wire. Okay, so this is the Z0. So that's why these two are called as the lossless lines. Mostly they will be using because they are having a very low loss. Okay, they are called as the lossless lines. So that's why we will use mostly the coaxial cables because it is producing a real impedance. Okay, what is that real impedance? Z0 is equals to 60 divided by root epsilon or L and B by A. Okay, suppose if you take a parallel wire, there also you will get loss is very low. Okay, so that's why we will use mostly these coaxial cables and parallel line wires. Now similarly, what will be the phase velocity of the wave in the line? The phase velocity of the wave, already you know phase velocity can be represented as Vp is equals to omega by beta. Okay, what is beta here? Beta is equals to omega root LC by comparing these two. So what omega by beta will be 1 divided by root LC. Already you know L into C is equals to mu epsilon. So you can write, right? So Vp is equals to, already you know this. But one more important next relation is 1 divided by root LC. Okay. So this is called as the phase velocity. Okay. Now one more important thing is the distortionless. Suppose if L by R is equals to C by C, C by Z, then this is called as the condition for the lossless and distortionless line. Okay. And you should remember that what is the distortionless line means the rising time, suppose if you take any harmonic, okay, the rising time constant must be equal to the falling time constant. Okay, the rising time constant must be equal to falling time constant, then that is called as the distortionless line. Okay, what is meant by this distortionless means the phase must be linear function of the variable. The phase must be linear function of the variable. Okay, that is called as a distortionless. So, what is the rising time constant? Suppose if you observe the transmission line, the structure of the transmission line, there will be series resistance and series inductance will be there, shunt capacitance and shunt conductance will be there. Okay, if you take the rising time constant is equal to falling time constant means, okay, if you take the rising time constant is equal to falling time constant means you are taking the time constant of the RL circuit and time constant of the RC circuit. Okay, means GC circuit. Okay, so the time constant of the RL circuit is L by R. The time constant of the RC circuit means CG circuit. GC circuit. Okay, C by G. Okay, so from this LC is equals to RC. So this is the condition for the lossless and distortionless line. And one more important thing is every lossless line is a distortionless line, but not vice versa. So every lossless line, if it is a lossless line, you can say that perfectly it is a distortionless line. But if you bring a distortionless line, you cannot say lossless line all the time. So that is the point, you should understand that. Okay, so these are the very, very important things, you should understand that. Suppose if you take a lossless line means what? Lossless line means alpha is 0, then gamma will be is equals to beta, J beta. Gamma will be is equals to J beta, right? If you are taking a lossless line means what will be the gamma? Gamma is purely imaginary. So gamma means J beta, right? Suppose if you want to write the Zin of a lossless line, the input impedance of a lossless line, what is the input impedance? Already you know, input impedance will be is equals to x, at x is equals to L, the Z of x is called as the input impedance. Suppose if you put in place of gamma, if you write J beta, and x is equals to L, because I am writing the input impedance. Input impedance means there must be x is equals to L, and also what is gamma? Gamma is equals to J beta, because I am talking about the lossless line. So you will get the expression like this: Zn is equals to Z0 ZL cos beta L plus Z0 sin beta L. And you should remember that, okay, there is cos h gamma L and sin h gamma L is there, right? Okay, so in place of if you write cos h j beta, you will get cos beta, sin h j beta, you will get sin beta, j sin beta. Okay, if you are writing cos h j beta, if you write gamma, right? Gamma is equals to what? J beta. Cos h j beta is equals to cos beta only. Okay, and sin h j beta can be written as j sin beta. Okay, if you note that, so you can easily write this. So Zn is equals to Z0 into ZL cos beta L plus Z0 sin beta L divided by Z0 cos beta L plus ZL sin beta L. So this is a very, very important expression. You should understand this. Okay, so now one very, very important thing here in the transmission line you should remember that is the impedance, the input impedance or impedance anywhere on the line is dependent on the distance from the load, the length of the line. Okay, it is always depending on the length of the line. It is always depending on the length of the line. So if you are talking about the impedance means, first of all you have to talk about the length of the line. So depending on the length of the line, the impedances will be varying because you cannot expect on the entire line you will be having a equal impedance, because RLGCs are different at different points on the line. So that's why you cannot expect same voltage on the line, you cannot expect same current on the line. Okay, so that's why you cannot expect the same impedance on the line. Okay, so that's why at different lengths will be having different impedances. Okay, suppose if you take x is equals to L, suppose L is equals to, suppose if you take lambda by 8 line, suppose if you are taking L is equals to lambda by 8, always the length of the line will be represented in terms of the wavelength. Okay, this is one common practice, so you should remember that. So always the length of the line is represented in terms of the wavelength. Suppose if the length is equal to the lambda by 8, means the length is represented in terms of the lambdas. Okay, wavelengths. So suppose if the length of the line L is equals to lambda by 8, now what will be the beta L? Beta L, now we are talking about the beta L, right? So beta L will be, what is beta? It is 2 pi by lambda, already we know. It is L is equals to how much? Lambda by 8, so you will get beta L, it will be pi by 4. Okay, pi by 4. So from this Zn will be equals to Z0 into ZL plus JZ0 divided by Z0 plus JZL. This is one result. And suppose if you write L is equals to lambda by 4, if you take a line of length lambda by 4, beta L will be equals to pi by 2. Now Zn is equals to Z0 square divided by ZL. This is called as the, so if you observe this, Zn is equals to Z0 square by ZL. Okay, suppose if you take any short circuited, observe this, suppose if you take any short circuited line means what? ZL is equals to 0. If ZL is equals to 0 in this, Zin will be infinity. Means if you are taking a short circuited line, the input impedance of that short circuit line will be become infinity, means open circuited nature. Suppose if you are taking any purely inductive line here, suppose if you are writing Zn is equals to Z0 square by ZL, the inductive line means what? J into something. Okay, inductive line means J into something. If you are writing that J into something in the denominator, means it will become a capacitive in nature. So that's why we are naming this one as impedance inverter. It is called as the impedance inverter. What is lambda by 4 line is also called as the impedance inverter. The input impedance of this line is Zn is equals to Z0 square by ZL. Okay. This is called as impedance inverter. Suppose if you take a lambda by 2 line, then beta L will be equals to pi, Zn is equals to ZL. Okay, so whatever you are putting the, suppose if the length of the line is, lambda by 2, if the length of the line is lambda by 2, okay, now whatever you are putting the ZL here, it will be appeared here. Okay, this is called as the impedance reflector. Okay, so now if L is equals to lambda, if the length of the line is equal to the lambda, now beta L is equals to 2 pi, now Zn is equals to 2L. So you have to put all these beta values here and you will get definitely this. So here if you put L is equals to lambda by 2 or L is equals to L, the beta L will be 2 pi, here beta L is equals to pi, here beta L is equals to 2 pi. For both the cases the input impedance will be ZL only, because sin pi and sin 2 pi are same, means 0, right? So that's why these are very very important. And very very important thing here is beta L. What is the beta L? Beta L is called as the, L is called as the physical length, beta L is called as the electrical length. Okay, L is called as the beta L is called as the physical length, L is called as the physical length, beta L is called as the electrical length. Okay, electrical length. And one more important thing is, what are the units of the physical length? Meters. What are the units of the physical length? What are the units of the physical length? Meters. What are the units of the electrical length? Electrical length units are, what this is electrical length, pi by 4 means radians or degrees. So you can represent this one, or radians or degrees. And one more important thing is, physical length is always, L is always less than beta L. So beta L is always less than physical length. Okay, you have to write, what is this? Physical length is always less than the beta L. So L physical is less than the L electrical. Okay, L will be less than beta L. So L is there. For this L, we have to multiply with 2 beta by lambda. Okay, so that's why physical length will be less than the electrical length. Okay, this is the very very important thing. So you have to focus on this. Okay, so here very important thing you have to understand, that is the impedance is dependent on the length of the line. Okay, the impedance is dependent on the length of the line, and also the impedance is also dependent on the frequency also. Okay, because the length is dependent on the lambda, means what? Frequency. Okay, lambda means it is 1 divided by frequency, inverse relation, right? So always as according to the frequency and according to the length, the impedance will be varying, and these are the very important things you should remember. Okay, and we will continue.